All right, so let's talk about finding the projection of a vector onto a subspace of a vector space. So here we have find the projection of B onto W, and W here is so we're finding this vector. W is the span of V, and V is the set minus 1, 0, 1, 0, 1, 1, 1, 0, and 0, 0, 1. And B is a vector in R4, 4, 1, 2, 1. And right, in the vector space we're working at here, orthogonal, is R4. All right, so a couple ways of doing this. One, we can use a formula, which you often see in a lot of linear algebra books, which is this one right here. Now, to use this formula, though, let me explain how the formula works. So you have a set of vectors that are orthogonal to each other. So v1, v2, v whatever number of vectors you have. They first of all have to be orthogonal for you to use this formula. So if they're not, you can use the Gram-Schmidt process. Okay. Now in this case, I have here in my note where I have note that the vectors in V, so just scribble that. Those vectors are all orthogonal to each other. So you can take the inner product or the dot product, whatever you want to call it here, and you would see that if you took the dot product between any of these two vectors, they would equal 0. So we can go ahead and use that formula that I have in the box. Essentially, the way the formula works is that you have these orthogonal vectors, v1, v2, v3, in your, or whatever number of vectors that are in your basis, and you dot them with the vector that you're taking the projection onto the space. So in this case, it's B. So basically, it'd be v1 dot B over v1 dot v1 of v1 plus v2 dot B over v2 dot v2 times the vector v2 plus v3b over v3 dot v3 times v3. And right, and for the bottom, you could also write that out where I have v1 dot v1, v2 dot v2. You could also write that in v3 dot v3. You can write that as the magnitude squared, because that's what that is, okay? And essentially, yeah, the way this would work is you would just take some dot products here, and yeah, v1, v2, and v3 dotted with v individually, and then the dot products of those orthogonal vectors with themselves, okay? And the projection vector here that we're looking for is just a combination of v1, v2, v3 with the coefficients being given by what I wrote up here, where I have v1 dot b over v1, v1. So that's all I did there, okay? I add this up, and then this is our final result here. Now, there's another way to do this, which is using matrices. So we have that the projection of B onto a subspace W is equal to the matrix A times A transpose A inverse times A transpose B, if this is the case of A transpose A inverse exists, of course. Now, the way it works with matrices is that you take a matrix, in this case A, and you want to make it so that the columns are the vectors of, the columns are the vectors that were given before where I wrote V. Okay, so you put them in a column, and I'm not going to go too much into why that is or how that works. The purpose of the video is just kind of like trusting me and doing these computations, showing you how the computations work. So you start with that, and then there's a bunch of ways of going about this, but what I like to do is to find what A transpose is, and then find what A transpose A is equal to, okay? And you should always get a square matrix. In this case, it's a 3 by 3 if you went ahead and did the computations. And then you would find the inverse of this matrix right here, which is here, and I didn't go through the steps because then you can find that. And finally, we're gonna go ahead and find this product. Maybe start with my tone there, you can maybe think, oh, this is supposed to be easy. Not necessarily. So we put ATA inverse, A transpose B, and then you multiply that out in any which way you want. Accordingly, we have that multiplication of matrices is associative. So, and I think what I did here was I did these two first, and and then I multiply these two next, and then finally that result times b, and I get that, and that your same exact answer as what I had up there. Okay, so both ways will work out. You know, the disadvantages and advantages. The advantages for the first method, I think it's, you know, nicer to work with. That's the advantage that I would see. The big disadvantage there, though, is that you have to make sure your vectors are orthogonal to each other. And if they're not, then you have to use Gram-Schmidt, for example, there. If, on the other hand, if you use this method, it's tedious, for sure. You have to figure out that you have to multiply a bunch of matrices together, find an inverse. But at the end of the day, you don't have to do any orthogonalization with like Gram-Schmidt. It's there ready for you. Okay, so either way, it's up to you. However, I've seen a lot of professors prefer the method that we have here. Okay, all right. Well, thank you for your time. Appreciate it.